In this lecture, we'll study Markov decision processes. Markov decision processes, or MDPs, are the stochastic decision-making models underlying the reinforcement learning problem. Reinforcement learning is essentially the problem when this underlying model itself or some parts of this model are unknown. And the agents not only need to make sequential decision, but it also needs to learn this model while making these decisions. But more on that later. First, let's understand what are Markov decision processes. Markov decision process, or MDP, is a formal model of sequential decision making which proceeds in discrete rounds. In every round, all the relevant information from the past is captured in the state of the process. The definition of state depends on the problem. Let's consider the example from the previous lecture about a robot who is trying to move from some point A to point B. In this example, the current state of the robot could be a combination of location of the robot, its current stance, for example, whether it's sitting or standing or moving, and its velocity if it is moving, and so on. The decision maker, which in this example is the robot controller, observes the current states and takes an action. For example, whether to lift a leg of the robot or move a limb forward. The reward signal and the next state depends both on the action taken and the state in which it was taken. For example, aggressively moving a leg may be a good action when the robot is walking or running, as it might make the robot move forward fast and earn reward. However, when the robot is still in a standing position, the same aggressive action may make the robot fall, and therefore it's not a good action. A defining property of MDPs is the Markov property, which essentially says that the future is independent of the past given the current state. This effectively means that all the relevant information in terms of determining the future reward in future states are captured by the state of an MDP. More formally, the Markov decision process proceeds in discrete rounds, starting in some initial state which we call S1 here. In every round T then, the agent first observes the current state, called S of T's here, takes an action AT, and then observes a reward signal that we call RT here. This reward depends both on the state of the agent and the action taken, and tells the agent whether the action taken was a good action to take in the current state or not. Finally, the process transitions to the next state, which we call ST of +1. The Markov property that I mentioned earlier is formally stated as the following two properties. Firstly, the next state, the probability of transitioning to a particular next state, depends only on the current state and the action taken in the current state, and not on any other aspect of the history. These probabilities are specified by a matrix P. Secondly, the expected reward at any time again depends only on the current state and the action taken in that state, and none of the other aspects of the history till time t. These rewards are specified by a matrix R, which gives the reward for every combination of state and action. The trade-off between immediate rewards and future rewards of the sequential decision problem in MDP and the need for planning ahead is captured by the goal of the MDP. At a high level, the goal always maximizes some form of cumulative rewards. There are three popular forms of cumulative rewards in literature: total reward, infinite time average reward, and discounted sum of rewards. Total reward is simply the sum of rewards in some finite time t. The infinite time average reward is averaged over a very large time horizon. So you may imagine that performance of the action in the few initial rounds doesn't really matter here. What we are looking for is a good asymptotic performance. And discounted sum of rewards is the weighted sum of rewards where the weights decrease with time as a factor of some gamma less than 1. This essentially means that the immediate returns are more valuable than those far in future. Discounted sum of reward is one of the most popular form of goals used in MDPs. This for many reasons. Firstly, it is mathematically convenient as it always converges and avoids the complication of infinite returns. And practically, depending on the application, immediate rewards may indeed be more valuable than those obtained far in future. More importantly, often, uncertainty about far future is not well understood, and therefore you may not want to give much weight to what you think you might earn in that far ahead in future. So to summarize, Markov decision process is specified by a tuple of 5 parameters. The space of states, which we denote here by capital S, a starting state from this space of states, the space of actions, which we denote here by capital A, the transition model, which is a Markovian transition model, is given by the transition probability matrix P, which gives for every state and action the distribution of the next state. The reward function R gives for expected reward for every state and action. Finally, an MDP specification may also include the definition of goal of the MDP and the discount factor gamma if one is used. Let's conclude this discussion with an example. Let's formulate a simple MDP for a robot moving on a line. Let's say there are 2 actions available to this robot. Walk, which means do some slow limb movements, which allows the robot to move 1 step without falling, or run, which involves aggressive limb movements, which may allow the robot to move 2 steps forward, but there is a 20% chance that it will make the robot fall. Once the robot falls, it cannot get up, and the goal is to move forward quickly and as much as possible without falling. So now let's model this example as an MDP. The first step is to define the space of states. We can define the state of the robot as a combination of its stance, meaning whether it's standing or whether it's fallen down, denoted here by S and F. And the other part of the state definition is the location of the robot on the line, represented here as 0, 1, 2, 3, 4, and 5. So this state S1 here, for example, means that this robot is standing upright in location 1. And the state F2 here means that the robot has fallen down on location 2. Now the robot starts in this standing state in the beginning of the line. So this here is your starting state. The action space consists of 2 actions, walk and run. Walk means slow limb movements and running means aggressive limb movements. The state transition depends both on the current state and the action taken. Walking in any of the standing states always transfers the robot to a state right next to it in terms of 1 location ahead. This is shown here by the black arrows. The action of walking never makes the robot fall down. On the other hand, the second action, the action of running, may make the robot move 2 steps ahead and transfer from S0 to S2 or S1 to S3, shown here by the green arrows. But that happens only with 80% of chance. With 20% chance, the robot may fall down and move to a fallen state. In the fallen state, there is no action that can take the robot get out of that state. As is often in the case of many applications of MDP, or more generally reinforcement learning, the rewards and the goals of the MDP are not exogenously given, but defining them are also part of the modeling process. Different settings of rewards and goals will lead to different interpretation of this problem. For example, let's say the reward is the number of steps that the agent moves as a result of an action. Now, if the goal is set to be the total reward, then the agent in this MDP should just always walk. If the agent always walks, it never falls, and the total number of steps, which is the goal, will be maximized by always walking. On the other hand, if the goal was set to be discounted reward, so that the initial steps that the robot moves are more important than the later steps, then it's important for the robot to move more steps initially, and therefore it may make sense to take the run action. One can also set the reward to be 0 for all the state except for the final state here, which may be the target to be reached. In this case, the discounted sum of rewards is simply gamma raised to tau, where tau is the time that the robot takes to reach the final state. Here, the agent would want to minimize tau, the time to reach the final state. Therefore, the agent may want to take the aggressive action of running so that it can quickly reach the target state. Another important point to note in this example is that in an MDP, an action can have long-term sequences. For instance, locally, it may seem beneficial to run even in the starting state, because even though there is a 20% chance of falling, with 80% chance of moving 2 steps ahead, the expected reward for running is 1.6 steps, which is more than the reward of 1 step for walking. However, this doesn't take into account the effect of this decision on future. So if we were thinking about discounted sum of rewards, we may have to consider the fact that running or taking an aggressive action may make the robot fall down, which will decrease the future rewards. Therefore, finding an optimal sequential decision-making strategy under an MDP involves a careful trade-off between immediate rewards and future rewards. In the next couple of lectures, we'll look at the problem of finding the optimal policy for an MDP.